Hi, my name is McGrath Gomez, and my student ID is 1252320. This is project number 3 for Professor Bautista in Calculus 1. So project number 3 is about the rates of change. It asks a pretty simple question. When a model is launched, the propellant burns for a few seconds, accelerating upward. After burnout, the rocket coasts upward for a while, then begins to fall. A small explosive charge pops out a parachute shortly after the rocket starts down. The parachute slows the rocket to keep it from breaking when it lands. The figure here shows the data from the flight of the model rocket, and then it says use the data to answer the question. So before we look at the questions, we first need to learn basically what is a derivative. Well, a derivative in its basic summary what it's going to tell us is it's going to tell us the instantaneous rate of change of one quantity within respect to another. So pretty much it's going to ask, and if we ask what is a derivative, it's going to tell us the instantaneous rate of change of one quantity with respect to another. To kind of summarize it, it's how fast something moves or changes in an exact moment. So how fast things change in an exact moment. Basically, it's going to answer these questions. How fast does it change? And how do you figure out what is a derivative? Well, the easiest way to figure out what a derivative is, it's basically the slope of tangent line, also known as the steepness of the line that touches the graph at a single point. So if we look at this little graph right here, we can see that it touches here. It touches here. It touches here. There's various locations that it touches. Basically, a tangent line is going to look something like this. So for this point, it's going to be something like that at a given point. So it's going to be that. Now a secant line is going to connect 2 points together. That's going to be secant. So that's the difference between the two. And basically, what is a derivative? It is the tangent line. Okay. Let's move on to our next point. How do we find a derivative? Well, we can find a derivative with something called, with an equation called differentiation. Sometimes a differentiation, it's a fancy word, but all it means is to take the derivative of, and it's going to look something like this. So f with a little mark on it of x. If you remember, f of x is usually a function, right? This can also be represented as like y, or sometimes you'll see y is equal to f of x. But a differentiation is going to be f, the little apostrophe, x. We call this prime. There's also another way you can write this. Another way to write this is going to be dy over dx. This is Leibniz. I believe it's called Leibniz form. So you might see it in f prime of x or Leibniz notation. So derivatives are basically the idea of limits. It has a foundation, and it comes from the idea of limits, the limits idea, where 2 points close on a graph close to each other get infinitely closer. So infinitely closer. And for this one, the slope is pretty much equal to the derivative. So the limit usually looks kind of like this. F prime of x lim, we use this notation, and then h approaches 0. F of x plus h minus f of x over h. We use this notation to find the derivatives, but it takes forever. So mathematicians kind of realize, like, hey, if we were to find, and if we were to use this every single time, it's going to take absolutely forever. So there's a couple of rules that they invented to take shortcuts. So some of the rules is called power rule. Basically, whenever you have the f prime of x over n, it's going to equal n times x and then n minus 1. And then you have the constant rule. Where f prime, let's say a number like 5. So any constant number, so it could be 0, 1, 2, 3, 4, 5. Any constant, it's always going to equal 0. So the easiest way to kind of memorize a power rule is to realize that if they ask you for maybe like if they ask you to take the derivative of, let's say, 6x squared, we can use this power rule. So it's going to be 2, it's this number right here, times 6x, and then x is going to be 2 minus 1. So which is going to give us 12x to the 1, to the first power, or just 12x. That's how the power rule works. There's also another rule that we can kind of learn. It's going to be called the product rule. Whenever you add stuff together, you can use the Leibniz notation. So basically, it is d over d of x. So it's f of x times g of x is equal to f prime x times g of x plus f of x times g prime of x. So whenever you have things that add, we will use the product rule. Sorry, whenever you have things that multiply, we will use the product rule. So this applies to pretty much any functions. And if you ask what is a function, well, functions kind of look like y is equal to, or sometimes even f of x is equal to x squared plus 2x plus 4. So the way you differentiate this is you take every single number. So you can do f prime. I like using f prime because it's a little bit simpler, of x squared. That we know we're taking the derivative of. And we're going to keep all these symbols the same. So nothing's going to change. And then 2x, so f prime, 2x, and then f prime of 4. So let's do the 4, because f prime of 4 is just 0. F prime of 2x is just 2. And f prime of x squared is just 2x. So we are going to be left with the f prime of x is equal to just 2x. Remember, we're keeping these two the same. So 2x plus 2. So that's how we differentiate a function. So there's product rule we can use whenever we multiply functions. And there's also something called a quotient rule. Whenever we divide or you see a fraction in a function. So the quotient rule is pretty much, we'll use Leibniz notation just to make it interesting. So d over dx of, let's say, f of x over g of x is equal to g of x times f prime x minus f of x times g prime of x over g of x squared. So that is probably the 4 most important rules that we need to memorize whenever we're learning derivatives. So the next question is, what is a ROC? So ROC is rate of change. It's basically how things change when another changes. The way you can kind of think rate of change, there's 2 different ones. There's average rate of change, and there's instantaneous. So whenever we think of an instantaneous, you can think of at an exact point aka the derivative, or the tangent line in respect to a point. The average rate is just over a given interval. So derivatives in my major, which is going to be electrical engineering, or any kind of engineering, the way you'd use it is whenever you have something like a current, it's always defined as I, or symbolizes I. And then you can find the rate of change represented by Q, and then over time, T. And you can get this equation. It's a very, very famous equation. It's called I over T. Sorry, of T is equal to the derivative of the rate of change of T over the derivative of T. So this formula basically just shows you how electrons can move quickly and they equal a large current. Or electrons can move slowly for a small current. That's how it ties into my major. Now, another thing that we got to learn really quick is acceleration. So this you can actually learn in a physics class. And usually during Physics 101, you will go over this. As higher up in physics you go, the more you'll learn about electricity, magnetism, so you'll use this. And same thing with acceleration. Usually acceleration in physics is something that speeds up, slows down, or changes direction. In math, we can kind of think of it as f prime. Now, we can always take another derivative of a derivative. So that's our velocity. So in physics, velocity is usually defined as a speed and direction. In math, we call it f, two quotation marks, which means the second f second prime, or f second derivative. And usually, the average velocity is just the slope of the secant line. If you remember correctly, the slope of the secant line, it's going to be like this. You get a curve. It's basically just going to be 2 points, say this and this is going to be the slope, and this is going to be your average rate of change. This is important because in physics, this is going to teach us how capacitors work. And inductors work. So now that we learned all of these, we can kind of go back to our very first problem. So we're looking at this graphically. So we can see how fast. Well, the first question asks, how fast was a rocket when the engine stopped? So if you use a red marker, we can see that this graph on this side is going to show the velocity. The velocity is going to increase, right? And then on the bottom side, it's going to show time in seconds, right? So how fast was a rocket when the engine stopped? Well, if you look at this point right here, the engine's going to keep accelerating, and you'll see that it hits a peak right over here. And that point is right on number 2. So it's 2, and it's roughly about 190. So on the velocity, it's going to show that it's at 190 feet per second. So that is our answer, 190 feet per second. And how many seconds did the engine burn? Well, if you look at the bottom, which I'll put in blue, the time after launch, you'll see that that peak crests at 2 seconds exactly. 2 seconds exactly. So it'll burn for about 2 seconds. And then, when did the rocket stop? So if we look at this graph, we can see that it peaks at 2 seconds and then it gradually goes down. It just gradually goes down, all the way down. Now, before it goes all the way down, you'll see that it hits a 0 velocity. Basically, your X point. This is where it's going to reach the highest point. Because remember, after it launches, there's enough momentum. So right now it's accelerating. There's enough momentum for it to keep going a little more forward. Not a lot, but there's a little bit more in terms of momentum. So it's still going up a little bit. So right over here, right in this graph, so this portion of it is negative velocity, right? Because it's going down. That's one way to think about it. And right over here, when it touches 0, it tells us that it's pretty much done climbing. So when did the rocket reach its highest point? Well, it reached its highest point at 8 seconds. And what was its velocity? Velocity was exactly at 0. And another way to kind of think about it, right? So if you're ever shooting a bullet out of a gun, right? Or a cannon. You have this cannonball that's going across. When it has the most energy, it's going to be right over here. This is the most kinetic energy. Right when it touches the ground, like right here, it has the least amount of kinetic energy. But you can see that it keeps going for a little while, even when it loses velocity. Like right here, when it peaks, it still keeps going for a little while. Just like that, the rocket also coasts. That is why at 0 velocity means that it's no longer really going, because after that it's going to keep going down. On the graph, It's going to keep going down. So we know that the velocity is going to be 0 because we can kind of see. Now, when the parachute popped out, how fast did it go? So after it coasts for a little while, it hit its peak, and then the small charge exploded. So when the small charge exploded, it's going to slow down the velocity, which I'm going to put in green. So right over here. So the little thing keeps going all the way till it hits roughly about like 10.8 seconds. So right over here. Right over here. So 10.8 seconds. And we can see that this is at negative 90 feet per second. Now it's negative 90 because it's falling down. So when did the rocket shoot out the parachute? The rocket shot out the parachute with a charge at 10.8 seconds. And how fast was the rocket falling? Well, the rocket was falling 90 feet per second. Whenever we give an answer, there is no negative and there is no positive, because if you flip the graph around, it's 90, but just in the opposite direction. So E asks, how long did the rocket fall before the parachute stopped? How long was it falling before the parachute opened? We can say that roughly about 8 seconds is right when the parachute was essentially deployed. So the easiest way to kind of put this is to take this number and subtract it. So 10.8 seconds minus 8 seconds is going to give us 2.8 seconds. So that's how long the rocket fell in this point right here before the parachute opened. So it was falling. So once it got past 0, it was falling. So when was the rocket's acceleration the greatest? Well, just like that cannonball that we have, the highest kinetic energy is right here. Right here. So right at that peak is when its acceleration was the greatest. 2 seconds. Now G asks, when was its acceleration constant? You see this line over here. That's a very constant slope that goes all the way from there straight down. From 2 seconds all the way to roughly about 10.8 seconds. So that is when it was constant. That is a little too bright. Let's do orange. 2 seconds to 10.8 seconds. Now, G has a second part to it. What was its value then? So to round off its value, what we need to do is we need to identify some intervals, right? So between these 2 points, so between 2 and 10.8 is when that constant slope is happening. So t is equal to 2 and t is equal to 10.8. Those are our two intervals. We're going to title one T1, another one T2. And what was the speed during then? Well, we kind of established it was going to be 90 feet per second, and this one's going to be 190 feet per second. T1, 90, sorry, T1 is going to be 190, and T2 is going to be 90. There's a formula we can use. So whenever we have the triangle, think of it as the rate of change. So your A is equal to the difference or the change of your velocity over your difference of time. So this is called delta. And delta represents basically the rate of change, or the difference. Is equal to V2 minus V1 over T2 minus T1. Another way to kind of see V as your Y value, right? Another way to kind of see your T is your X value, right? Because we're on the X-intercept, right? Because this is an X and that's a Y, and this is an X and that's a Y. So if we do the two together, so you're going to get so 90, negative 90 minus 190 over 10.8 minus 2. It's going to give us 280, negative 280 over 8.8, or roughly about negative 31.881 feet per second. So if we round this to the nearest integer, it's going to give us negative 32 feet per second. I hope this kind of helps and shows how you can find the answers to the questions after they ask us. This is a pretty cool question. It's going to come in handy in physics, and it's going to come in handy in any kind of engineering. So thank you, Professor Bell, for giving us this lecture, and also Organic Chemistry Tutor to help me learn this. I used Professor Bao's 3.4 chapter and Organic Chemistry Tutor on the video on the rates of change involving calculus. Thank you so much. I will see you next time. Take care.